Okay, let's dive in. We're looking at the source material you sent us, focusing on polygons today.
Yeah, exactly. So the plan is to unpack these pages, find the real core ideas about what polygons are, how they're defined.
And some of those angle properties, which look pretty interesting in your notes.
Right. It all comes directly from the material you gave us. It might seem basic geometry, but there are some, well, specific rules and neat properties hiding in there.
Definitely. Let's get started. So first up, the absolute basics from your sources. What is a polygon?
Okay, so definition-wise, it's a closed shape, flat, on a plane, and made only of straight line segments.
And those segments have strict rules, right? The sources seem to really emphasize this.
They do. Two big things. The segments, or sides, can only touch each other right at their endpoints.
Okay.
And each endpoint, which we call a vertex, exactly two segments have to meet there. No more, no less.
Oh, okay. So that's why some shapes look like polygons but aren't. Your sources had examples.
Exactly. Like if lines cross inside the shape, that's out. Or if a vertex connects, say, 3 lines, nope.
Or if it's not even closed, just a wiggly line.
Right. Those examples really help clarify why the definition is so precise. It has to follow all those rules.
Got it. Segments are sides, endpoints are vertices. Makes sense.
And, they get names based on the number of sides. Your material lists the common ones. Triangle for 3, quadrilateral for 4, pentagon, hexagon.
Octagon, decagon, yeah. And the sources also talk about 2 main types, convex and concave.
That's right. Convex is where all the inside angles are less than 180 degrees. Think of a normal-looking polygon.
Okay.
Concave means at least one angle pokes inwards, basically.
Yeah.
It's bigger than 180 degrees. Your notes mention that usually polygon implies convex, unless they say otherwise.
Right. And they defined a diagonal, too, just a line connecting 2 vertices that aren't already connected by a side.
Yeah, non-consecutive vertices. Now, the angles. This is where your sources lay out some really elegant stuff, especially for the sum of the interior angles.
Oh, yeah, this part was neat. The trick of picking one vertex.
Pick one vertex, draw all the possible diagonals from that single point.
And it slices the polygon up into triangles. Right?
Exactly. And there's a pattern, which your sources point out. If the polygon has n sides, it always makes n2 triangles using this method.
Always n minus 2 triangles.
Always. And since every triangle always has angles adding up to 180 degrees, well, the total sum of the interior angles in an n-sided polygon is just n2 times 180.
That's a powerful little formula straight from your pages. Simple multiplication.
It is. But then there are the exterior angles. If you imagine walking around the polygon and extending each side as you go.
Right, the angle you turn at each corner.
Yes. And the sources highlight this amazing fact. The sum of those exterior angles, one at each vertex, is always 360 degrees.
Always. Doesn't matter how many sides.
Doesn't matter at all. Triangle, square, hundredagon. The total turn is always a full circle, 360 degrees. It's a fundamental property mentioned right there in your material.
Wow, okay. That's simpler than the interior sum.
Definitely. And this leads nicely into regular polygons, which your sources also cover specifically.
Right, the perfect ones. All sides equal length.
And all interior angles equal, which also means all the exterior angles must be equal too.
Okay, so if everything's equal, finding the measure of just one angle is doable.
Yeah, it's straightforward. For a regular n-sided polygon, each interior angle is just that total sum we found. N2, 180, divided by the number of sides, n.
Makes sense. Total divided by how many there are.
And for the exterior angles, it's even easier, since the total is always 360.
Ah, so each exterior angle is just 360 divided by n.
Precisely, 360 n. And your sources also note that handy relationship. Any interior angle plus the exterior angle right next to it always adds up to 180 degrees. They form a straight line if you extend the side.
Okay.
Which gives you that useful trick mentioned in the examples. If you know just one angle, interior-exterior, of a regular polygon, you can figure out n, the number of sides, usually using that 360 exterior angle formula.
Very neat. So wrapping it up from the sources you provided, we have the core definition, the strict rules for sides and vertices, the convex-concave types, how to find the sum of interior angles using triangles.
That constant 360 sum for exterior angles, and then the specific formulas for angles in regular polygons where everything's equal.
It covers the essentials really well.
And maybe a final thought, looking back at those rules and formulas, especially from the examples in your material, the math has consequences. That N2 180 formula, or the 360 one.
Yeah.
Well, and the number of sides. Has to be a whole number, right?
Right.
And at least 3. You can't have 4.7 sides.
Right, obviously.
So It means not just any angle sum is possible for a polygon. Not just any angle measure is possible for a regular polygon. The geometry itself, described in these sources, dictates that it must work out to be a valid integer for a real polygon to exist with those properties.
Huh. So the angle rules actually constrain what kinds of polygons can even exist. That's actually pretty deep. Something to think about next time you see a tiled floor or a honeycomb.
Exactly. Gives you a new perspective, maybe.